Welcome everyone to this deep dive into Retrieval-Augmented Generation, commonly known as RAG. Today, we are going to explore how modern AI systems are able to go beyond what they were originally trained on and actually pull in fresh external knowledge to answer your questions more accurately. This presentation is designed as a beginner to intermediate guide, so whether you are completely new to this concept or you have heard the term RAG being thrown around in AI conversations without fully understanding it, this session will walk you through everything step by step. By the end of this video, you will understand not just what RAG is, but how it actually works internally, what tools power it, and why so many companies today are relying on it to build trustworthy AI applications. Let's begin with the fundamental question: what exactly is RAG? In simple terms, RAG connects a language model to an external knowledge source at the exact moment it is generating an answer. Instead of the model relying purely on what it memorized during training, the system first retrieves relevant documents or pieces of information from an outside source and then feeds that retrieved content to the model before it produces its final response. This is a crucial distinction because it means the model isn't just guessing based on old training data, it is actively looking things up, much like a human would search through reference material before answering a tricky question. Now, why does this matter so much? The biggest benefit is that answers stay current. Since the knowledge source can be updated independently of the model, the AI can reflect real-time or recently added information without the company needing to retrain their entire model, which is expensive and time-consuming. Additionally, because the answers are grounded in a real documents, the AI becomes far less likely to hallucinate, meaning it is far less likely to confidently state something that is simply false. This approach has several real-world use cases. First, consider chatbots. Many companies build support and internal assistants that can cite their own company documentation directly when answering employee or customer questions, making the responses accurate and traceable. Second thing, second thing about search and question answering system. Instead of just giving you a list of links like a traditional search engine, a RAG powered system can directly answer your question using semantic search, understanding the meaning behind your query rather than just matching keywords. Third, RAG is heavily used in knowledge systems within legal, medical, and research fields where professionals need to look up precise facts from large bodies of documents quickly and reliably. So, before we go uh, further into how RAG works, it is important to understand the actual problems that RAG was designed to solve. Traditional large language models, even though they are incredibly powerful, suffer from a few core limitations. The first major issue is hallucination. This is when a model confidently states facts that are wrong or completely made up, because the model is essentially predicting the most statistically likely next words based on patterns it learned during training. It doesn't actually know if something is true. It just knows what sounds plausible. This becomes a serious problem in situations where factual accuracy really matters, such as legal or medical context. The second issue is the lack of real-time knowledge. A language model once trained cannot see today's news, cannot access your private company files, and cannot know about live updates happening in the world right now. It is essentially frozen at the point when its training ended. This leads directly into the third problem: static training data. Every model has a training cutoff date. and beyond that date, its knowledge simply does not exist. Over time, as the world changes, the model's understanding slowly becomes outdated or stale, even though it might still sound confident when answering. RAG directly addresses all three of these problems by grounding every single answer is retrieved, verifiable sources. Instead of relying purely on memorized patterns, the model is given actual reference material at the time of answering, which dramatically improve both accuracy and trustworthiness. Now, what is a RAG pipeline? Okay, so now let's define what a RAG pipeline actually is in a more technical sense. A RAG pipeline is a workflow that retrieves relevant information first and only then lets the language model generate an answer using the retrieved context. In essence, it is a combination of two separate capabilities, search and generation, merged into a single seamless process. To make this easier to understand, let's use a simple analogy. Think of a library. Imagine the entire process happening in three steps, just like a visit to a library. In the first step, a visitor walks up with a question they want answered. In our system, this represents the user query, the actual question that a person types into the AI application. In the second step, the librarian goes and finds the most relevant books related to that question, fetching only the few books that are actually useful rather than bringing back the entire library. In our system, this role is played by the retriever working together with the knowledge base, searching through a large collection of documents and pulling out only the most relevant pieces. In the third and final step, an assistant reads through those page books and writes a clear, well-formed reply based on what was found. This is exactly the role of the generator, which in most modern systems is a large language model. So the entire RAG pipeline can be thought of as this three-step library visit: ask, fetch, and answer. Core component of RAG, the four building blocks. Every every RAG system, no matter how complex it eventually becomes, is built on four fundamental building blocks, and understanding each one clearly is essential before we move into the workflow. The first component is the retriever. Its job is to search through the knowledge base and return the chunks of text that are most relevant to whatever question the user is asking. Think of it as a search engine sitting inside the pipeline. The second component is the vector database. This is a specialized type of database designed to store embeddings, which are numeric representations of text, and to perform extremely fast similarity searches across potentially millions of these embeddings. Popular examples include FAISS and Pinecone, both of which we will explore in more detail shortly. The third component is embeddings themselves. Embeddings are what turn ordinary text into numeric vectors, essentially converting words and sentences into a mathematical form that captures their underlying meaning. This is the technology that allows a computer to understand that two pieces of text are conceptually similar even if they don't share the exact same words. The fourth and final component is the generator, which in almost all modern implementations is a large language model. Its job is to take the retrieved context along with the original question and write the final natural language answer that the user actually sees. Together, these four components, a retriever, vector database, embeddings, and generator, form the backbone of every RAG system. Now, note that we understand building blocks. Let's walk through exactly how they work together in sequence step by step, from the moment a user asks a question to the moment they receive a grounded answer. Step 1 is the user query. This is simply the moment when the user types or speaks their question into the system. Step 2 is embedding. The query itself gets converted into a vector using the same embedding technique we discussed earlier, so that it can be mathematically compared against the documents stored in the vector database. Step 3 is retrieval. The system searches the vector database and pull out the top k most relevant chunks of text where k is simply the number of results we want. For example, the top 3 of top 5 most relevant pieces of information. Step 4 is context injection. These retrieved chunks are then added directly into the prompt that will sent to the language model, essentially giving the model extra reference material to work with before it responds. Step 5 is the LLM response. The language model now generates its final answer, and because that answer is based on the injected context, it comes out grounded and in many implementations even cited back to its source. It's also worth mentioning something that happens before any of this: an offline ingestion process that occurs just once, ahead of time. In this process, documents are broken into smaller chunks, converted into embeddings, and indexed inside the vector database so that everything is ready and waiting before any actual query ever arrives. Embeddings and vector databases, the memory that makes retrieval work. Let's go a bit deeper into embeddings, since they are really the foundation that makes intelligent retrieval possible. An embedding is essentially text turned into numbers. Each chunk of text gets converted into what's called a dense vector, something like a long list of decimal numbers, for example, values like 0.12, negative 0.45, 0.78, and so on. The key magic here is that similar meanings end up landing close together in this numeric space. For instance, the word king would end up mathematically close to the word queen, while both would be far away from an unrelated word like bicycle. Depending on the specific embedding model being used, these vectors typically range anywhere from 384 to 1536 dimensions, and each of these dimensions helps capture some nuance of semantic meaning. Now, once you have these embeddings, you need somewhere to store and search through them efficiently. And that's exactly where vector databases come in. They are purpose-built for extremely fast similarity search across potentially massive collections of vectors. Let's look at a few of the most popular options. FAISS is Meta's in-memory library, and it is widely considered the workhorse of the research community due to its speed and flexibility. Pinecone, on the other hand, is a fully managed cloud-native solution, meaning companies can use it in production without having to manage any of the underlying infrastructure themselves. Waviate is an open source server that comes with hybrid search built directly into it, combining both semantic and keyword based matching. And finally, Chroma and Melvus round out the list. Chroma is often favored for lightweight, quick prototyping, while Melvus is built to scale all the way up to billions of vectors for every large production systems. Retrieval and prompt augmentation, finding the right context, then using it. Now let's understand exactly how the retriever decides which pieces of information are actually the best matches for a given query. The core idea here revolves around something called cosine similarity, which is simply a mathematical way of scoring how close two vectors point in the same direction. The closer the point, the more similar the underlying meaning is considered to be. When the system performs search, it typically returns what is called the top k results, meaning it fetches the k number of closest matching chunks. Commonly, this might be set to a range like 3 to 5 results. To make this searching process fast even when dealing with enormous datasets, systems relying on something called ANN indexes or approximate nearest neighbor indexes, with HNSW being one of the most common techniques used to keep search speeds practical even at huge scale. Once the most relevant chunks have been retrieved, the next step is prompt augmentation, and it's worth comparing what happens before versus after this technique is applied. Before augmentation, if you simply ask a bare question like, "What is our refund window?" the model has no choice but to guess an answer based on whatever it happened to memorize during training, which could easily be outdated or simply wrong. After augmentation, however, the system first inserts the actual relevant context directly into the prompt. For example, a line stating that refunds are accepted within 30 days, and only then ask the question. The result is a response that is accurate and can be directly traced back to a real, verifiable source rather than being a guess. Now, the generator and an end-to-end example context aware answering in action. So let's now focus on the final piece of the puzzle, the generator. The generator, which is the large language model at the heart of the system, reads both the retrieved context and the original question together, and then it writes a natural language answer based on that combined information. Because the underlying facts are coming from real retrieved sources rather than pure memory, the replies produced are both context aware and traceable back to their origin. To make this concrete, let's walk through a complete end-to-end example using a company chatbot that answers questions from internal documents. Imagine an employee asks, "How many vacation days do I get in year one?" In the first step, this question is captured as a query. In the second step, called retrieval, the system searches through the company's HR handbook, which has been stored inside a vector store, looking for the sections that closely match the employee's question. In the third step, called augmentation, the system takes the matching policy paragraph it found and injects it directly into the prompt that will be sent to the language model. Finally, in the fourth step, called generation, the language model produces its reply, in this case stating 15 days, and it is able to cite the exact section of the handbook that this answer came from, giving the employee full confidence that the answer is accurate and verifiable. Advantages and limitations, a balanced view. Like any technology, RAG comes with a clear set of advantages as well as some real limitations. And it's important to understand both sides so you can make informed decisions about when and how to use it. On the advantages side, first, there is significantly less hallucination because answers are grounded in real retrieved sources rather than pure model memory. Second, there is a real-time knowledge. You can simply swap out or update the underlying data without needing to retrain the entire model. Third, RAG is cost effective compared to fine tuning, since updating the knowledge base can be done in minutes rather than requiring an expensive and lengthy retraining process. Fourth, RAG provides source attribution, meaning the replies you receive can actually be traced back and trusted, since you can see exactly where the information came from. On the limitation side, first there is latency because every single query now requires an additional retrieval step before the model can even begin generating its answer, which adds some processing time. Second, the quality of retrieval is absolutely decisive if the retriever pulls back poor or irrelevant matches. The final answer will also be poor, no matter how good the language model itself is. Third, there is a complex setup involved. Since you need to properly handle chunking documents, generating embeddings, and building and tuning the indexing system. Fourth, there is an ongoing cost consideration since every request now includes extra context tokens that need to be processed, which adds to the overall computational expense. It's worth noting just how widely adopted this approach has become. Currently, 51% of enterprise generative AI deployments already use a RAG in production, making it the most popular grounding approach used by companies today. RAG versus fine tuning, when to use which. A very common question that comes up is when should you use RAG and when should you use fine tuning instead? Let's compare these two approaches directly across several important aspects. When it comes to what each approach is best suited for, RAG excels at injecting facts and fresh knowledge into a model's responses, while fine-tuning is better suited for changing the style, tone, and overall behavior of a model. When it comes to updating data, RAG can be updated in just minutes simply by re-indexing new documents, whereas fine-tuning requires hours or even days to retrain the model. In terms of freshness, RAG remains always current because it retrieves live information at query time, while fine-tuning is frozen at whatever point the training happened. When it comes to cost, RAG generally has a low upfront cost with only a small additional cost per query, whereas fine-tuning involves a high upfront training cost but becomes cheap to run afterward. And finally, in terms of source citations, RAG is able to provide traceable answers that point back to their original source, while fine-tuning backs all of its knowledge directly into the model's weights, meaning there is no way to trace an answer back to a specific source. The general rule of thumb to remember here is simple. If you need the model to know specific facts, use RAG. If you need the model to behave differently, use fine tuning. And very often in real world applications, companies actually end up using both approaches together to get best of each. Tools and technologies, the modern RAG stack. Let's now look at the actual tools and technologies that developers use to build these RAG systems in practice. First, we have LangChain, which is an orchestration framework that provides chains, agents, memory management, and integrations with more than 50 vector stores, making it one of the most popular frameworks for building complex AI applications. Second, we have Llama Index, which is a retrieval focused framework that specializes in deep indexing capabilities and powerful query engines, making it particularly well suited for applications where a retrieval quality is the top priority. Third, we have OpenAI APIs, which provides both the embeddings and the language models that power the generation step of the pipeline. And fourth, we have vector databases as a category including the ones we discussed earlier, Face, Pinecone, Waviate, Chroma, and Malvus, all of which serve the purpose of actually storing the knowledge in a searchable form. In practice, a very common pattern that developers follow is to combine LangChain or Llama Index for orchestration, pair it with an embeddings model, and connect it to a vector database. And remarkably, this entire pipeline can often be assembled in just a few lines of code thanks to how mature these tools have become. Advanced concepts and the future of RAG, where the field is heading. As RAG has matured, several advanced techniques have emerged that push its capabilities even further. The first is hybrid search, which blends semantic vector-based matching with traditional keyword matching techniques such as BM25, allowing systems to achieve more precise recall by capturing both the meaning and the exact keywords in a query. The second is re-ranking, where a cross-encoder model rescores the initial set of retrieved results, pushing the precision of the final results above 90% in many implementations. The third is multimodal RAG, which extends retrieval beyond just text, allowing systems to retrieve across images, audio, and even code, all within a single unified retrieval space. Looking ahead, the future of RAG is heading in some exciting directions. One major trend is agentic RAG, where AI agents themselves decide when to retrieve information, what to retrieve, and how to use it, enabling much more sophisticated multi-step reasoning rather than a single simple retrieve and generate cycle. Another major trend is enterprise AI, where permission-aware knowledge layers are being built to power secure company assistants that respect who is allowed to see what documents. And finally, there is the concept of autonomous knowledge, where self-updating systems continuously keep the underlying knowledge base fresh without requiring manual intervention. Summary and key takeaways, the big picture in one glance. Let's now bring everything together with a quick summary of the key takeaways from this entire presentation. First, RAG grounds AI by combining retrieval and generation. The system is able to produce answers that are accurate, up to date, and properly cited. Second, there are four core parts that make this possible: embeddings, the vector database, the retriever, and the LLM generator, all working together in harmony. Third, RAG fixes fundamental LLM gaps. It significantly cuts down on hallucination and stale knowledge, and it does this without requiring a retraining of the underlying model. Fourth, RAG is both practical and involving. It is already powered by mature tools like LangChain and various vector databases today, and it continues to evolve toward more advanced concepts like agentic RAG in the future. To recap the entire flow one final time in a simple sequence, it starts with a query, then the query gets embedded, then relevant information is retrieved, then that information is used to augment the prompt, and finally the model generates its answer. Query, embed, retrieve, augment, generate. That's the complete rec cycle in 5 simple words. Thank you so much for watching this complete walkthrough of Retrieval-Augmented Generation. As we've seen throughout this presentation, RAG represents a genuinely smarter approach to building AI systems, one that keeps responses grounded in a real verifiable knowledge rather than relying purely on what a model memorized during training. I really hope this breakdown has made the entire concept clear and easy to understand for you. If you have any question or thoughts, please feel free to drop them in the comment section, and I'll be happy to discuss them with you. Thank you once again for your time, and I'll see you in the next video.